They move in silence, hidden in crates that breathe, not the kind of cargo you'd expect to see crossing jungle trails or slipping through narrow backroads on the edge of a rainforest. These are cold-blooded passengers, hundreds of snakes, each one alive, each one demanding a controlled environment as complex as any refrigerated produce shipment. From the outside, it looks like a stack of wooden boxes on a motorcycle, but inside, there's a fragile ecosystem that must remain perfectly calibrated. Because in this kind of transport, the real threat isn't motion, it's the lack of it. What carries these animals safely through unpredictable terrain is not instinct, but engineering. Technologies originally designed for fruit preservation are now being reimagined for ectothermic life. The same thermal envelope systems used to protect mangoes and avocados from spoilage are now stabilizing the temperatures inside snake crates. Engineers map heat flow, measure metabolic thresholds, and calculate insulation thickness. Not for produce, but for pythons. It's agroengineering adapted to an unusual challenge, transporting muscular, temperature-sensitive reptiles through environments that can fluctuate more than 10 degrees Celsius in a single hour. But temperature is only the beginning. Vibration matters. Noise matters. Sudden shocks or stillness can trigger a stress response that silently raises mortality risk. That's why modern crates borrow principles from precision agriculture, especially seed dispensers. Those machines learned long ago how to release fragile seeds into the soil without damaging them. The same idea applies here. Crate floors float on dampening mechanisms, reducing mechanical trauma and diffusing sudden jolts during rough transport. Every snake, in a sense, is being carried as carefully as a grain of wheat in a high-tech planter. Airflow, too, is a form of life support. Inside these crates, oxygen must circulate like in an underground tunnel, and that's not a metaphor. Designers looked to mining ventilation shafts for inspiration, studying how air is directed through narrow, enclosed, and high-risk spaces. The results? Crates now integrate micro-ventilation systems that regulate internal humidity and remove heat pockets, just like the airflow channels that protect miners beneath the earth. It's a hidden choreography of fans, filters, and structural geometry, all aimed at keeping the interior of a box stable enough for life. And here lies the paradox. While most animals suffer from excessive motion, snakes suffer from the opposite. If the airflow stops, if the box becomes too still, too closed, the internal climate breaks down. Heat stagnates, humidity spikes, respiration slows. In a box of 40 snakes, even 5 minutes of thermal imbalance can begin a chain reaction. That's why logistics for reptiles aren't built around speed alone. They're built around dynamic equilibrium. Movement, when controlled, becomes a form of ventilation. To visualize all this, picture a split screen. On one side, a deep mining tunnel with airflow vectors pulsing through a dark corridor. On the other, a thermal simulation of a crate packed with snakes, where air paths bend around the coils of living bodies. Both systems are designed to protect life in confined spaces. Both are vulnerable to failure if the balance shifts by just a few degrees. This is what most people never see, the invisible calculations behind an ancient practice, now infused with modern precision. Snake transport isn't about danger. It's about maintaining life, silently, across impossible distances. There's a reason reptiles bask in the sun. They don't generate heat, they borrow it. And that biological dependence becomes a ticking clock when a snake enters a sealed container. Inside a transport crate, temperature isn't just a condition. It's a survival threshold. A deviation of just 2 degrees from the optimal range can push a snake's metabolism into shock. It's not dramatic. It's not loud. But it is fatal. And the source of the threat isn't always the jungle or the road. Often, it's the crate itself. Most failures in snake transport come down to thermal drift. When insulation fails or heat pockets form, the animal's body responds with a chain of invisible reactions. Slowed heart rate, decreased oxygen uptake, cellular stress. The ambient temperature doesn't have to collapse completely. Just a gradual drift outside the critical 24 to 30 degree C window is enough to begin metabolic failure. What looks like a mild change on a thermometer can become a point of no return for an animal built around thermal precision. But new materials are changing that. Engineers are now integrating phase change compounds, known as PCMs, into crate walls and compartments. These materials absorb and release heat at targeted thresholds, acting like a biological buffer that stabilizes the internal climate. When the surrounding environment heats up, the PCM absorbs excess energy. When it cools, it releases stored warmth. It's a passive system, but extremely effective, because it doesn't rely on batteries or motors. It relies on physics, calibrated to reptilian biology. The result? A crate that thinks thermally, one that reacts to the world outside not with wires or programming, but with the silent intelligence of molecular transition. And when deployed correctly, the difference is profound. In Southeast Asia, exporters tracked snake mortality over hundreds of shipments. The pattern was clear. 87% of in-transit deaths weren't from injuries, impact, or overhandling. They were from temperature fluctuation. The enemy wasn't visible. It was statistical, chemical, and entirely preventable. In one operation, deep in the forests of Malaysia, a small team made a quiet change. They added PCM panels to the bamboo crates used to transport native pythons. The journey would take 12 hours across uneven terrain and shifting microclimates. Before the modification, they expected up to 15% loss. After, 0 fatalities. Every animal arrived alive. The crate had become a mobile terrarium, not by chance, but by thermal engineering. And that's the underlying truth. In snake transport, thermodynamics is the true apex predator. A few grams of material can mean the difference between life and collapse. The snakes move because of their muscles, but they survive because of the crate's ability to manage invisible forces. Heat gradients, humidity vectors, energy diffusion. Every moment inside that container is a negotiation between physics and biology. So when people imagine snake transport as a raw, instinct-driven activity, they miss what really matters. It's not the chase, it's not the capture, it's not even the route. It's the unbroken sequence of thermal balance maintained hour after hour through crates designed not just to carry, but to protect. Because in this journey, the biggest threat doesn't hiss. It waits in silence, 2 degrees away from disaster. A crate full of snakes isn't just cargo, it's a biome in motion. Beneath the wooden slats and canvas straps lies something more complex than stacked weight. It's layered muscle, live respiration, and active temperature regulation, all compressed into compartments that travel through dust, heat, and unpredictable terrain. But unlike boxes of grain or pallets of fruit, you can't just stack and tie down, because the wrong angle, the wrong pressure, the wrong moment of stillness can turn a stacked crate into a silent trap. The risk begins at the base layer. Snakes, when packed incorrectly, face more than discomfort. The coiling of their bodies is essential for their breathing. When stacked too tightly or without airflow corridors, the bottom layers experience rising carbon dioxide, decreased ventilation, and slow respiratory failure. They don't scream. They don't resist. They simply slow down until they stop. And the damage doesn't stop with one animal. A poorly designed crate affects every layer. To solve this, engineers turned to modular thinking. Crates are now designed with compartmentalized levels, each separated by a flexible membrane that adapts to the animal's movement. These aren't rigid partitions. They bend and adjust, maintaining structural space while respecting the snake's own flexibility. It's a kind of mechanical empathy, a structure that listens to muscle, not just mass. The partitions maintain consistent airflow, reduce compression zones, and allow for micro-adjustments as the cargo shifts. And the results are measurable. In the Brazilian Amazon, a route known for dense forests and uneven roads, handlers tested this new crate design over a 3-month cycle. With airflow spacers and flexible compartments in place, deaths from compression dropped by 39%. But something else happened too. Loading and unloading became faster. The animals arrived in better condition, more active, and with cleaner skin, improving market value by over 15% in some cases. Efficiency wasn't just technical, it became biological. In Ecuador, this thinking evolved even further. An indigenous cooperative restructured their entire crate system after studying banana transport tunnels. They observed how bananas are shipped in high humidity corridors with open vent geometry, allowing airflow without exposure. That model, soft-sided tunnels with cross-ventilation, became the inspiration for their snake crates. The result wasn't just safer travel, it was more consistent breathing patterns, more active movement during unloading, and healthier muscle tone upon arrival. What began as a fruit logistics solution became a reptile transportation innovation, because stacking, in this context, is not a matter of efficiency, it's a biological dialogue, a negotiation with dozens of bodies that move, flex, and breathe, even in stillness. Every crate is a vertical ecosystem, layered in muscle, air, and thermal logic. Designing for that complexity means rethinking the idea of weight. Not just how much the crate carries, but how it carries life itself. In the end, a crate isn't a box. It's a suspended environment. Every surface, every layer, every vent is part of a system engineered to allow living cargo to travel without dying. And that's the shift. From containment to cohabitation, from pressure to flow, from stacking to sculpting space that moves and breathes along the way. From the outside, it still looks like a hunting trip. A motorcycle winding through dense vegetation, crates balanced with ropes, faces weathered by sun and sweat. But inside each container, a quiet revolution is unfolding, one that replaces fear with calculation and instinct with design. Reptile transport, once a raw survival operation, is now a study in precision agriculture. The crate has become a biosystem, and the handler, a technician of mobile ecosystems. Each box is more than packaging. It's a thermoregulated environment, calibrated to reptilian biology. Like a moving terrarium, it balances not just temperature, but humidity, airflow, and vibration. It reacts to changing conditions not with guesswork, but with systems adapted from other agricultural domains. Cold chain logistics, greenhouse ventilation, even post-harvest nutrient retention. The goal isn't simply to arrive, it's to arrive alive, functional, and intact. And the systems are evolving. In Thailand, one company has integrated GPS tracking with environmental sensors directly into their crates. These crates measure internal temperature, humidity levels, and even motion frequency, then transmit that data in real time. A technician in an office, hundreds of kilometers away, can adjust ventilation protocols mid-journey. If a heat spike is detected in a roadside rest zone, the crate's microventilation adjusts automatically. The crate becomes its own pilot, its own climate guardian, its own sensor-equipped sanctuary. It may sound excessive, all this infrastructure for animals that were once carried in sacks or woven baskets, but the results speak in both survival rates and economic returns. Fewer losses, better muscle condition, higher sale prices in urban markets, and above all, consistency, because markets don't run on luck, they run on predictability. And that predictability now depends on the same kind of technology used to ship pharmaceutical products, tropical fruit, and premium seafood. But the real story isn't the sensors or the materials, it's the mindset behind them. The quiet understanding that snakes aren't just wild, they're alive, and life in transit is fragile. Every curve of the road, every pause in motion, every fluctuation in humidity, it all adds up, not in seconds, but in cellular stress. What looks like still cargo is in fact a living system adjusting, breathing, responding to an engineered environment designed for it to survive. Transporting snakes isn't an act of danger. It's an act of coordination between physics and biology, between the instinct of the hunter and the logic of the engineer. Each crate is a bridge between ancient knowledge and modern control, where temperature is monitored like currency and air, like time, must never run out. Across rivers, forests, and backroads, the journey seems raw, but beneath each crate of snakes lies a quiet orchestration. What appears simple is, in fact, engineered survival. Crates functioning as mobile ecosystems, preserving life through airflow, thermal control, and biomechanical structure. Inside, nothing is left to chance. Temperature is regulated by phase change materials. Air moves through calibrated corridors, inspired by mining shafts. Crate floors absorb vibration like precision seeders. All of it tuned to reptilian biology, not spectacle. The result is subtle. The snake arrives. It breathes. But that moment is the product of logistics shaped by biology and restraint. Systems designed not for show, but for stability. This is where agriculture and engineering converge, transforming unpredictable terrain into a controlled passage for living cargo. No fanfare, no improvisation, just precision, quiet, constant, and invisible to most. Because the most complex logistics don't roar. They hum beneath the surface, turning a wooden box into a breathing corridor through space and time. And that's the future. Not wild, but calculated. Not chaotic, but deliberate. A silent symphony that moves life forward.